Alright, this is the first video of a series that will discuss acids and bases. It says here Unit 8. I believe this is actually, however, Unit 9. In this first video, we'll just talk about general features of acids and bases, and we'll talk about naming acids and bases, and then we'll also talk about, well, there are a number of different theories of acids and bases. And when I say theories, I don't mean the theory like the theory of gravity, but it's more of a model and more of a way in thinking about acids and bases. And so the first one is called the Arrhenius acid-base theory, named after, I believe he was Swedish, Svante Arrhenius. He's also the first person to link the greenhouse effect to carbon dioxide. This was back in the 1800s, so the whole thing about global warming and carbon dioxide has been known for quite a long time. Anyway, that was Arrhenius. And then we'll also talk about, well, that's in this video, and we'll talk about another acid-base theory called the Bronsted-Lowry acid-base theory. There's actually one other, but we won't get to that in this course. Alright, so Arrhenius acids. Right? Arrhenius defined acids as essentially compounds that contain hydrogen ions. So when you dissolve these compounds in water, they produce hydrogen ions. So you can say Arrhenius acids are compounds that contain the hydrogen ion. That's the H+ ion. And I will elaborate on this in a little bit, but remember, let's just talk about the hydrogen atom for a moment. The hydrogen atom, right? It's element number 1, right? It's got one proton in the nucleus, and so there's a nucleus, and then on the outside of the nucleus we have an electron, and that's it. There is a different isotope of hydrogen, deuterium, that has both a proton and a neutron in the nucleus. But most hydrogen is hydrogen 1, and it's got just one proton in the nucleus. Now, if we lose that electron, so this is a hydrogen atom, so right here, atom. If we lose that electron, all we have left is a proton. This is the hydrogen ion. So the hydrogen ion is really the same thing as a proton. And in the next the next lecture in this series, we'll talk about the Bronsted-Lowry definition, and we'll talk a lot about protons. Hydrogen ions, protons are essentially interchangeable. Right. So they produce ions in solution, so hence they are electrolytes. Electrolytes are nothing more than ions in solution. It's getting warmer now when people go outside and they they exercise and whatnot. They need sports drinks to replace their electrolytes. They're drinking specific electrolytes that are required for muscle contraction and whatnot. But to a chemist, any ion in solution is an electrolyte. And again, the reason we call them electrolytes is because these guys, see if I can squeeze it in here, they conduct electricity. So pure water actually does not conduct electricity, but you never really have pure water, and at least not outside the laboratory. And so you always want to keep electrical devices and water separate, because it's not really the water that's conducting electricity, it's the dissolved ions in the solution that conduct electricity. Also, ions have a sour taste. They turn litmus red, and they neutralize bases. Now, litmus is what we call an acid-base indicator, and it is a compound indicator. It is a compound that changes colors based upon whether it's an acid or base, and we can talk maybe more about that later on. Acids also neutralize bases. So one of the double displacement reactions that we had talked about way back when was this neutralization reaction. You take an acid and a base, you combine them, and you get a salt and water. And we'll look at this reaction more specifically a little bit later. Alright, now as far as naming acids go, most acids are going to end in the suffix "ic", acid. All right. Now if you look at the periodic table, right? Let's just look at the halogens. There's fluorine, chlorine, bromine, and iodine, right? This is group 7, and they all form a minus. It's a -1 ion. So if we stick a hydrogen in front of it, right, +1, -1 for fluorine, chlorine, bromine, iodine, we get the compound HF. And so we refer to this as hydro, and we don't say chlorine, we say chloric. So it's hydrofluoric, hydrochloric, hydrobromic, hydroiodic. HF is hydrofluoric, and it's spelled FLU, fluoric acid. HCl, may have used this in the laboratory, hydrochloric acid. Hydrochloric acid, by the way, is the same thing as stomach acid or gastric acid. So you actually make this stuff, your body makes this, and that acid is used to help digest proteins when you eat a hamburger or whatnot. All right, bromine, this would be HBr, and it's hydrobromic acid. Bromic acid. And the last one, HI, we're not saying high, HI is hydroiodic acid. So they all begin with hydro when we say fluoric, chloric, bromic, and iodic acid. All right. Now some acids are combined with a polyatomic ion, and I'm not going to ask you to know I'm not going to ask you to know chloric acid or chlorous acid or perchloric acid. There are a number of other acids that you need to know, but these are not them. We're not going to talk about these two. But a number of the other acids have polyatomic ion associated with them. These, by the way, these are referred to as binary acids or halo acids because they all contain a hydrogen, or a binary acid because bi for 2, there's just 2 atoms. But if you've got a polyatomic ion, it gets a little bit more complicated. Let's take a look at those in the next slide. All right, so the ones that I asked you to know, I'll highlight here: hydrochloric, hydrobromic, also HF, hydrofluoric, and hydroiodic, just all those halo acids. Then we also have nitric acid. Nitric acid is a very common acid used in the laboratory, and we use the nitrate ion. So we don't say hydrogen nitrate, it's nitric acid. You don't need to know nitrous acid, so I'm just going to cross that off. And then there's sulfuric acid, H2SO4. This is battery acid, right? This is what you find in your car battery. And the polyatomic ion here is a sulfate. We don't say hydrogen sulfate, we say sulfuric acid. Again, there's another flavor, if you wish, of an acid, but we don't have the sulfate ion, we have the sulfite. That's sulfurous acid. We're not going to deal with that guy. But you do need to know carbonic acid, right? Combining with the carbonate ion. So carbonic acid, this is what's formed when carbon dioxide dissolves in water. You find this in any carbonated beverage like beer or soda. Phosphoric acid, you should know, combining hydrogens with the phosphate. Chloric and chlorus, you don't need to know. Acetic acid, I want you to know. So now there's a number of different ways of drawing the formula for acetic acid. And what I'm going to do is I'm going to take this ion here, and I'm going to draw every single atom the way it is attached. So this CH3, we have a carbon with 3 hydrogens attached, and then another carbon, and then it's double bonded to an oxygen and double bonded to another oxygen. Now, one of the things you may remember is that oxygen normally forms 2 bonds, but when it forms only 1 bond like this, you can put the unshared electron pairs in here, you'll find that it has a negative charge. On this oxygen, we just have 2 lone pairs or unshared pairs. Here we have 3, and the oxygen has a negative charge. All right, so this is one way of looking at, this is the acetate ion. The acid here, I'll use black. If we put a hydrogen on here, right, it's C double bond O, OH, COOH. This is now acetic acid. So you often see acetic acid drawn this way, CH3COOH. Very rarely will you see it drawn this way because it's just too cumbersome. But another way you might see it in your text is they might have drawn the acetate ion like this. C2H3O2, right? C2, 2 carbons, H3, 1, 2, 3 hydrogens, and then O2, and then they stick a hydrogen on in front. So it would be H, C2, H3, O2. All right. Now this brings up another interesting or important concept. There's something called, well, if you notice here, the haloacids, they all have just one hydrogen in front. So all these guys have a hydrogen in front. So if we draw the acetic acid like this, then we put the hydrogen in front. But it's really this hydrogen here that we refer to as the acidic hydrogen. These guys here are not. You notice in the acetate ion, these three are covalently bonded. This one here can come off and give you the acetate ion. So this is the acidic hydrogen, just as if I draw it this way, this hydrogen in front is. So the acetic acid, I'll put it here, a monoprotic, we use the term protic. Remember, protic sounds like proton maybe. A proton is what? A proton is a hydrogen ion. So monoprotic, 1 proton. Diprotic, triprotic, and you can have more, but most of these, well, the most that we'll go up to is triprotic. So HCl, HBr, HF, HI, these are all monoprotic. They all just have one monoprotic, 1 hydrogen. Nitric acid, also just 1 hydrogen, so monoprotic. Sulfuric acid, right, there's 2 hydrogens here, so now this is diprotic. Carbonic acid, 2 hydrogens, also H2CO3. This is also diprotic. Phosphoric acid, 3 hydrogens, triprotic. And what about acetic acid? It's just this guy in the end. It's not these 3 here. This is the only acidic hydrogen, so this guy is also monoprotic. So that's a little bit of a tricky one. So you should know the names, the formulas, and whether they're monoprotic, diprotic, or triprotic. All right, now bases. Bases, right? Arrhenius bases. Arrhenius bases produce hydroxide ions in water, and typically what that means is the chemical formula also contains hydroxide ions. So I'm going to put up here most, I'll say, contain the hydroxide ions. So for example, NaOH, sodium hydroxide, right? That's a base. Unlike acids that taste sour, bases taste bitter. They're also electrolytes. They produce ions in solution, right? We have sodium hydroxide here. You put it in water, you get sodium ions and hydroxide ions. Okay. They neutralize acids, right? You have an acid and a base, gives you salt and water, and they turn litmus blue. So, unlike acids, acids turn litmus red. Here I'm using a blue pen. Bases turn litmus blue. So, before we get any further, let me talk about this neutralization reaction. Again, really quick. You have an acid, and we can use HCl for the acid. We can add to that a base, and remember base blue, so we can use NaOH, and these guys will react, so HCl, NaOH, and this is a double displacement reaction if you recall. You switch out the 2 cations. The sodium is now going to combine with the chlorine, so we get NaCl, sodium chloride, or table salt. This is a salt, plus hydrogen combines with the hydroxide. I'm going to write it as H2O, but you might help to remember this is HOH. So you get a salt and water. Now, one thing, now this is table salt. We've all used table salt, but you can have other types of salt. So, for example, we can have, say, nitric acid and potassium hydroxide. This will give us a salt. This will give us potassium nitrate. And H combines with OH to give us water, H2O. This is a salt as well, but the name of this salt, well, okay, sodium chloride, this is table salt. Right. Some salts have specific names, you know, sodium chloride is table salt. Potassium nitrate is also a salt that has a particular name. This is known as saltpeter, and it is a ingredient in gunpowder. And it's mined out of the ground, similar to how sodium chloride can be mined out of the ground. All right, so that's the neutralization reactions. Let me talk a little bit about this litmus stuff. So litmus is as I mentioned before, is an acid-base indicator. And most indicators are also acids. So I'm going to write it as H and then IND for indicators. This isn't HIND, this is H indicator. And what these will do, we won't get into the details on how this happens. I'm going to have to draw equilibrium arrows here as well because this reaction can go back and forth. What can happen is the hydrogen ion can come off because it's an acid, and then you have the indicator. And so what happens is, depending upon, we can talk more about pH later, but if the hydrogen is attached, it might be one color. So that would be, say for example with litmus, if the hydrogen is attached, it's red. If the hydrogen comes off, we remove the hydrogen, it's actually, I should have a minus sign there, plus minus, right? This is now blue. So it changes colors depending upon whether the hydrogen is attached or not. And clearly I didn't draw the structure, the chemical structure of the litmus, but there's all sorts of different acid-base indicators. There's with the litmus, of course, there's bromocresol green, there's bromphenol blue, there's phenolphthalein, and just a whole host of different acid-base indicators. They're simply compounds that happen to be acids, but their color changes depending upon whether that hydrogen ion is attached or not. All right, so naming common bases. Yeah, sodium hydroxide, potassium, barium. Now notice some of these, like barium, is in group 2, so it's a +2 ion. So we're going to need, put here, right, barium is going to be +2. So barium is going to be +2, so we're going to need 2 hydroxides to neutralize it. Aluminum is in group 3, it's going to need 3. Iron can be +2 or +3. In this case, it's iron 3, right? So iron 3 hydroxide has 3 hydroxides. The 3 here again refers to, remember, the +3 charge on the iron, right? That's what that 3 is. All right, now there's another common base. So to figure out if it's a base or not, just look to see if it has a hydroxide on it, pretty much. There is one other, now that gets more complicated if you get into higher level chemistry, but for right now I'm just going to give you one, and sometimes you'll see it drawn this way. Ammonium hydroxide, okay, whoops, ammonium hydroxide, clearly a base. It has the hydroxide ion, but this is actually a misnomer. Misnomer means it's misnamed. Ammonium hydroxide doesn't actually exist. Now you might see this on some reagent bottles just for convenience sake, but actually what this is ammonia. Now ammonia is a gas. If we dissolve it in water, it would be aqueous. So this is ammonia gas dissolved in water. All right, so it's ammonia gas dissolved in water, aqueous ammonia. That's the same thing as ammonium hydroxide. Now if I write it this way, it's really clear that it's a hydroxide ion, and this is how Arrhenius would view ammonium hydroxide. You dissolve this in water, you get ammonium ions and hydroxide ions. Right? Well, that's what bases do. You dissolve in water, you get hydroxide ions. but it actually doesn't exist like that, and that will lead us into our other acid-base theory, the Bronsted-Lowry acid-base theory, where we talk about ammonia. All right, just to review, know these common characteristics of acids and bases. Bronsted-Lowry acid-base theory we haven't gotten to yet, so maybe we'll revisit this slide in the next lecture. Don't worry about that just now, but Arrhenius acids, right, produce hydrogen ions. Arrhenius bases produce hydroxide ions. They both electrolytes. The taste is important. Now, you're never going to taste anything in the laboratory, right? No eating or drinking in the laboratory. But if you taste a food that's sour, well, that means it's acidic, right? If you taste a food that's bitter or chalky, that means it's basic. So what kind of chalky foods? Well, if you take an antacid like Tums or Rolaids or something like that, it kind of tastes chalky. And I won't get into the chemistry behind it, but it's a base, and its point is to neutralize this excess stomach acid. So acids taste bitter, acids taste sour, and you see Calvin here puckered up. If you like take a bite into a lemon, right, they're acidic. And bases taste blucky, bitter. Now, acids don't really have a characteristic feel to them. They may sting if you have an open sore and on your finger or something like that, and the acid gets in there, but generally not. If you get in your eye, of course it'll sting. Bases, just because of the opposite of acids, don't think that they're not dangerous. The reason they feel soapy or slippery is they're actually dissolving the oils in your skin. There's a chemical reaction going on there, and that reaction you'll study if you take biochemistry. It's something called saponification or soap making. And so what's happening here is if you get a base on you and it starts to feel slippery or soapy, it's actually kind of reacting with your skin and flesh, and it can damage skin just like acids can. I already talked about limus. Phenolphthalein, this is commonly used in acid-base titrations. I think in the acid-base titration lab I had you do for the simulation, we used a different acid-base indicator, but here it's actually colorless in acid, so this means when it has the hydrogen attached. Okay, so phenolphthalein is our indicator, and when the hydrogen is attached, it's colorless, so I'll just use black for that. And when the hydrogen comes off, right, so here's the hydrogen. Whoops, I should make the hydrogen black. In this case, the hydrogen black. Then this indicator turns pink or red. That's phenolphthalein, another common acid-base indicator. So that will do it for this first lecture. The next lecture we'll discuss these Bronsted-Lowry acid-base theories, and we'll pick up there.